Hello and good afternoon. My name is Daniela Philippe from Hoare Lea, and I'm going to talk to you about the development and commissioning of one of the world's largest four-sided acoustic enclosures. This enclosure was designed for the ground testing of engines of some of the largest and loudest commercial and military aircraft after they have undergone maintenance at Cambridge Airport. The ground-run enclosure is 74 meters wide by 92 meters long. Its side and back walls consist of 20-meter high composite perforated metal panels with Class A sound-absorbent treatment on the aircraft side. The front wall is made of two doors, each comprising full-height, 2-meter thick acoustic louvers designed to allow the non-turbulent flow of up to 2 tons of air per second into the enclosure. Each door weighs approximately 200 tons and is electrically driven. A metal blast deflector is also present at the rear of the enclosure to smoothly direct propulsion air efflux upwards and prevent turbulent air recirculation back into the test volume. Once construction was completed, the next big step was the acoustic and aerodynamic commissioning of the enclosure. The design of the GRE was based on noise emissions of a Boeing 777-300ER jet and the Lockheed C-130J turboprop. This meant that upon completion, testing of the GRE with these two aircraft types was required. Obtaining a C-130J turboprop aircraft for the measurements was relatively easy. Sourcing a Boeing 777-300ER, on the other hand, was significantly more challenging. A shortage of jet aircraft at the time of the measurements meant we could not get our hands on one of these. Therefore, we hired a Boeing 767-200SF in its place, all the way from Turkey. With our noise sources sorted, we could start the acoustic commissioning process. The methodology for the measurements evolved quite significantly. It culminated in measurements at a total of 9 locations around and in the GRE, the use of 21 sound level meters, the development of in-house software to access all of the sound level meters simultaneously, optimized measurement stations to allow speedy deployment, and the use of approximately 1 kilometers of Ethernet cables. On top of this, we had a team of more than 50 people on site to help us. The first commissioning tests were carried out with the C-130J aircraft. The rigorous and meticulous planning proved its worth. With the aircraft engines run up to maximum power, the real-time analysis of the measurement data enabled immediate confirmation of compliance with the agreed limits. The testing of the alternative jet aircraft was not, however, as straightforward. First, as the target noise limits used in the design of the GRE were based on a Boeing 777, and as we couldn't get one for the measurements, we needed to determine new target noise limits based on the Boeing 767. This resulted in the need to carry out new free-field measurements to determine the source levels. Ideally, the revised compliance limits would have been determined before the GRE tests. However, operational issues dictated that the aircraft needed to be installed in the GRE upon arrival. Once the aircraft was in place, all of the monitoring systems were then deployed and the noise measurements completed without any data loss. Once the aircraft was taxied to the open runway, the monitoring stations were disassembled and redeployed, the free-field measurements were completed, and the results converted into compliance limits. Comparison with the in-GRE measurements revealed the unthinkable. The GRE was apparently non-compliant. An explanation was demanded, and quickly. The day and night before the measurements, there was a lot of heavy rain. The ground had become completely waterlogged. And as the temperatures rose during the day of the measurements, they caused the water on the ground to evaporate. But how did this affect the results exactly? The aircraft was placed on the runway with an array of microphones at approximately 150 meters from its center. The microphones were located at both 1.5 and 4 meters above ground. With this setup, we expected sound waves to travel in a straight line from the aircraft to the two measurement heights. We also expected a difference of not more than 5 dB between the two microphones, given the relatively small height difference. The evaporative temperature gradient caused a strong negative sound speed gradient. This led to significant differences in sound pressure levels between the two measurement heights. So, in summary, a strong sound speed gradient resulting from very specific weather conditions was concluded to be the cause of the GRE non-compliance. As soon as the weather allowed, the free-field measurements were repeated and the noise compliance limits recalculated for comparison with the in-GRE measurements. The GRE successfully passed all noise compliance tests, but not without a few sleepless nights for all of those involved.